Okay, the next lab we're going to be doing is one dealing with colligative properties, specifically the colligative properties that have to do with freezing point depression. You have freezing point depression at boiling point elevation. We're going to deal with freezing point depression, and we're going to really deal with determining the molar mass of a compound based on how much of a freezing point depression we get when adding an amount of that compound to an amount of a solvent that we have inside there. So let's go through some of the calculations. Then we'll go through the lab. There are going to be changes. I'm going to change the way we're going to do the lab compared to the way they have it in the module. And that's just to make it easier for you and just makes more sense, makes less mess. The way they do it doesn't really make a lot of sense. And this is a lab that we do almost exactly the same lab when we do it on campus during our normal GChem 2 stuff. So let's go through this for colligative properties. So the equation for the freezing point depression we're given is delta T is capital K, lowercase f, that's the constant, freezing point constant, times M, which has to do with molality, and then I, which is called the Van Hoff factor. We'll go through each one of these. I put a negative sign on the delta T. You'll notice in the handout that mine has a negative T on there. Why? Well, if we're doing delta T, delta means final minus initial. Final in this case would be the temperature of the solution. The solution, that is the mixture of both the solvent and the solute. And that would be minus the freezing point of the pure solvent. Okay, well, let's say we're dealing with water. Pure solvent, water normally freezes at 0 degrees Celsius, right? So this would be 0 degrees Celsius. So let's say our change in T, and let's say this reduces it down to negative 1 degree Celsius. Negative 1 degrees Celsius. Negative 1 degrees minus 0 degrees says our change in temperature is negative 1 degree Celsius. Okay, that makes perfect sense. The change in temperature is 1 degree Celsius. The problem is K is given as a positive. It's not given as a negative value, like it should. M is a positive value. I is a positive value. You multiply these together, you're never going to get a negative number. So you can't have this calculate that because that's a negative number and this isn't going to produce a negative number. So they should have put a negative on all the freezing point depression constants, but they didn't. So in place of that, I put a negative out here in front of the delta T to compensate for that. You're not going to see it that way anywhere else. You don't have to do it that way, but that's the way I do it. So let's go through each one of these things. Freezing point depression constant, as you would think, that's just a constant. Typically, a lot of things are proportional to other things, and then you need a proportionality constant to make it equal, and that's what the freezing point depression constant is for. Now, the big thing about this is the freezing point depression constant is for the solvent, not the solute you're adding to the solvent. This goes with the solvent. Okay, so make sure when you look it up on a table or whatever, you use the freezing point depression constant that is for the solvent you're dealing with. M, lowercase m, is molality. That's different than capital M, which is molarity. What is the difference? Well, molality is the number of moles per kilogram of solvent. Molarity is the number of moles per liter of solution. Solution is after you've mixed the moles in with the solvent. So this doesn't have to be, in other words, I might start off with 998 milliliters, and after I add the moles in, I have 1 liter of solution. Here, we don't know what the total volume of the solution is afterwards because it goes by kilogram of solvent. That's what it goes by, kilogram of solvent, not liters of solution. That makes a huge difference in there. So, and then the final thing is this I, that's the Van Hoff factor. The Van Hoff factor comes into play when this says the number of moles. When it says number of moles here, they're talking about the number of moles of a compound. Okay, that's moles of the compound. If we're dealing with an ionic compounds go into aqueous solutions as their ions. Therefore, the number of moles of, say, sodium chloride, if I put 1 mole of sodium chloride into water, that gives me 1 mole of sodium plus and 1 mole of chloride minus. Therefore, I end up with 2 moles of things. And that has to be accounted for because the colligative properties go by the moles of things, not the moles of compound necessarily, if it's an ionic compound. It could be moles of small particles of dust, moles of little teeny tiny stones you put in there, whatever it is, that's what affects colligative properties. And I don't have enough time to go through exactly why doing these things depresses the freezing point or elevates the boiling point, but suffice it to say it's a number of things. So in this case, the Van Hoff factor would be equal to 2, and that would account for the fact that 1 mole of this actually produces 2 moles of things. If it was magnesium chloride, then it would be Van Hoff factor of 3, because this goes to give me magnesium 2 plus 2 Cl minuses, so 1 mole of this gives 1 mole of this and 2 moles of that. Okay, even though you couldn't see what I was doing, I will try to pay attention to that. I've got it down a little bit more so you can see it quite easily, but if it was magnesium chloride, that Van Hoff factor would be 3, because 1 mole of this, 1 mole of this would give me 1 mole of this and 2 moles of the chloride in there. Okay, we don't have to worry about the Van Hoff factor for this lab. Doesn't come into play because the compound we're dealing with doesn't ionize or anything like that. So where would you get Kf from? You get Kf from a table like this, and remember it's for the solvent, not for the solute. It doesn't matter what you're putting into the solution, it is the kilograms of solvent, so that the Kf values that you have here go with that solvent. I wish they had given them as negative values, but they did not. Okay? So there's a couple of examples in the handout that I've given you, put up on there, that hopefully you've looked at, and it goes through the calculations of how to do it. And you can use that to help you with the calculations in this lab. But let's go through and work an example to make sure we can do this sort of things. So the first one is going to require the Van Hoff factor, and you're not going to need that in the lab, but I want you to be able to see how you could use that. So this one tells us, this is for example of problem number 1, and it tells us that there's 10 grams of sodium sulfate. So you remember from GChem 1 you had to memorize and learn your nomenclature, and you had to memorize your polyatomic anions. So this is where that comes into. What is sodium sulfate? Well, sodium sulfate, because you remember sulfate is SO4 2 minus, that polyatomic anion, there must be 2 sodiums on it. Therefore, when sodium sulfate dissolves into aqueous solution, we get 2 Na pluses plus 1 SO4 2 minus. Therefore, in this, our Van Hoff factor would be 3. Okay, so we have to use this for this problem. You won't have to do this sort of thing for what you're doing in class. So we always start with the definition of molality, and the definition of molality is moles of solute over kilogram of solvent. So, to be able to solve this problem, what it says, we want to know what the freezing point of the new mixture is. We want to know what the molality of the mixture is and calculate the freezing point. Well, if we look up on the table, we know that the, I want to find the right one for the table. We know that the Kf for water, and again, remember we're doing the Kf's go with the solvent. In this case, water is the solvent. We know it's going to be 1.86 degrees Celsius per mole. Okay, so we have to put the units on everything to make sure it works out. So we've got 1.86 degrees Celsius per mole, like that. All right. So first thing we need to do is figure out how many moles of sodium sulfate we have. They give us the molar mass of it, and it tells us that the molar mass is equal to 142.04. That's grams per mole, of course. So we have 10.0 grams of sodium sulfate, and we use our conversion factor. It tells us 1 mole. Remember what we want, we put on top of sodium sulfate. Has a mass of 142.04 grams of sodium sulfate. What we want to get rid of goes underneath. Now, you notice that this is given, the molar mass here is given in grams per mole. I'm using it in moles per gram. when you flip these things over to use it as your conversion factor, remember the number has to stay with the units. You can't you can't flip it upside down and keep the number on top. Since the number's with the grams and I want grams on the bottom, the number has to be on the bottom. That way grams of sodium sulfate cancel out, and I end up calculating out that there is 7.040 times 10 to the negative 2 moles of my sodium sulfate. Okay? Then I want to figure out how many kilograms of solvent I have. Well, it tells me that this is all done in 252 milliliters of water. So that's milliliters, that's not grams, that's not a mass. There are some things that you should always know as you go through the rest of your life. In case you get stuck on Gilligan's Island and everybody's looking at you to make the coconut radio, you got to have some values in your head that you can pull out to be able to do those things. And one of them is the density of water. And it's really easy because the density of water is considered to be 1 gram per milliliter, okay, for pure water. And this we're dealing with, we're going to say is pure water. So if there's 252 milliliters, and our density is 1 gram per milliliter, there must be 252 grams of water. But remember, our definition says kilograms of solvent. So we have to convert that, and we do that by putting 1 kilogram is 1,000 grams, and therefore there must be 0.252 kilograms of H2O. Okay, so I've got my bottom of my molality. My molality is going to be number of moles over top of 0.252 kilograms of H2O. So now I just got to get the number of moles. Well, how do I get the number of moles? Well, that's pretty easy. They told me I've got it. I already got the number of moles right there. We already did that. I kind of forgot we already did that. Super 40 times 10 to the negative 2 moles. So my molality, which is going to be moles per kilogram of solvent, in there is going to be equal to 2.794 times 10 to the negative 1. Little n for molality. That's my molality that I have. All right, well then I can figure out what my freezing point depression must be. All I have to do is write my equation. Negative T is equal to Kf, which I know is 1.86, times M and I. So that means negative delta T is equal to 1.86 degrees Celsius per mole times my 2.794 times 10 to the negative 1 mole. Mole cancels out, times my Van Hoff factor, which in this case is 3. If I calculate that all together, that means a negative delta T value I've got is 1.559 degrees Celsius, which means that negative delta T is equal to final temperature, which is the 1.559 degrees Celsius, minus the original freezing point, which was 0.0 degrees Celsius, and that means that's going to give us 1.559 degrees Celsius. But that's the negative of delta T, therefore my new temperature must be equal to negative 1.56 degrees Celsius. And that would be my final answer. So I got my molality, I got my freezing point depression. The new freezing point is negative 1.56 degrees Celsius. Okay? All right. What we're going to do in this lab, though, of course, is we're going to calculate out something that allows us to determine the molar mass. So let's do one like that. Even though this is a little bit easy, the one you're doing in lab is not that difficult either. So let's do it. That's number 2. We're going to have determine the molar mass of an unknown non-ionic substance. Non-ionic means it's not going to dissociate into ions. Therefore, Van Hoff factor is 1, and we don't have to worry about it. Same as you're going to do in the lab. Van Hoff factor is 1, don't worry about it. And it contains 30.0 grams of a substance per kilogram of water. Okay, so we're doing it on a per kilogram basis. That means we've got 1 kilogram of water, and it has 30 grams of substance in it, and our freezing point temperature is going to be negative 0.93 degrees Celsius. Of course, we know since this is water, 1.86 degrees Celsius per mole is what we're going to use there. All right, so that tells us that we're going to go with negative delta T is going to be equal to Kf Mi. We don't know what M is. But that's what we're going to solve for. Because if we can solve for M, remember, what's the definition of M? M is equal to number of moles per kilogram of solvent. Well, we have 1 kilogram of solvent, right? So that means molality is going to be equal to the number of moles that must have been put into our substance. We have the grams of substance that went in. If we can figure out the number of moles of substance, then we've got molar mass, right? Because what is molar mass? Molar mass is equal to grams per mole. So we've got the grams already, we just need to figure out the moles. So we'll plug in our values here, and that tells us, we rearrange this equation, this tells us that M is equal to negative delta T, freezing point, divided by Kf. Well, we know that the negative delta T, the negative of the delta T, and delta T up here is given as negative 0.98, is negative 0.93 degrees Celsius, and all that's divided by 1.86 degrees Celsius per mole. Well, degrees Celsius cancel out, mole comes up, that's going to give us the value, and we end up with 0.500 mole. Well, again, that's the molar mass. Molar mass is equal to the moles, that was 30.0 grams per kilogram of water, and this is 0.50 moles per kilogram of water. Kilograms of water cancels out, and we have 30 grams over 0.5 moles. We end up with a molar mass of 60 grams per mole. And it really is that easy. It's going to be a little bit different for what you need to do, because you're not going to have a kilogram of solvent. You're going to have probably around 3 grams. And if we have 3 grams, we're going to take that 1 kilogram is going to be equal to 1,000 grams. So 3 grams is like 0.003 kilograms, right? 1, 2, 3 in there. But that's okay. You just take it and figure out the mole. That's going to give it to you per kilogram of basis, and then you'll be able to figure out the molar mass. They show examples of how to do the calculations in the lab module. We're going to do the lab a little bit different than what they have inside there. So let's go through it and make sure that we're doing the changes the way they should be done. So first thing they do is they have you mass out approximately 3 grams of lauric acid. It's approximately 3 grams. Don't worry about getting it exact. It's more important that you have exactly how much you put in, not that it's exactly 3 grams. So if you end up with 2.9 grams, good enough. You put 2.9 grams into a weigh boat, take that weigh boat and carefully transfer that into your test tube that you have for there, and then put it on the rack. You got some water, and you want to heat that water up to just to below boiling, right? You don't want it to be 100 degrees Celsius. You want it to be a little over 80 degrees Celsius, so that when you put the test tube in it, you can get the lauric acid to dissolve. What you could do is get it to boiling, then shut it off, take it off of the heat substance, let it cool down some, take your thermometer and put it into the test tube with the lauric acid. Obviously, the lauric acid is solid at this point, so it won't go way down in there, but just set it on top of there. And holding the test tube and the thermometer in your hand so it doesn't fall, you can put the test tube into the hot water and swirl it around and pay attention to the lauric acid. It will start to melt, just like candle wax, same thing. It will start to melt, and then you'll be able to get the thermometer down in there. And once it melts enough, you get the thermometer in there, stir it with the thermometer, and keep stirring it, and read the thermometer, and get it to where the temperature gets up to at least 80 degrees Celsius. Okay, you want it to be at least 80 degrees Celsius. Then take it out of the hot water, set the hot water aside because you're going to use it again, and take your thermometer and keep stirring the test tube. The reason you have to keep stirring the test tube is the heat loss is on the outside of the test tube, and so it's going to cool there first, And if you're not stirring it, the lauric acid cools on the outside of the test tube, and then it actually freezes there, and it makes a insulation which keeps the center of it from actually freezing, and so you get a bias in the readings that you're doing. So once it gets down to, what do they say, 65 degrees, start recording the temperature. Be stirring it a little bit with the thermometer, and then every 30 seconds write down what the temperature is. Okay, and you have to be very, very careful reading this temperature. You can't just take a quick look at it and assume that you have it. You want to read that temperature as carefully as possible. If your thermometer has divisions on it that are every tenth of a degree, right? If this is like, 80 degrees here, 80.0, if this was 81.0, then you want to make sure that you look at that thing and try to estimate it to a tenth of a division. If the divisions, sorry, I didn't draw that correctly, it would be like 81 degrees here, and it would be like 80 degrees here, and it's somewhere in between. Try and estimate it to 1/10 of those divisions, so that you would say that that is at 80.5 degrees Celsius, okay? And keep taking those readings, stirring it every 30 seconds until you get 4 consecutive readings that are the same. It has to be exactly the same. Be really, really careful doing these readings. Don't do it really loosey-goosey. That won't take very long. It won't take very long. And you'll notice that as it's getting cooled down like that, it's going to start crystallizing. You're going to see crystals forming inside there as you stir it around, and it starts crystallizing. So you put that data in your data sheet. Now they tell you to dump out the lauric acid and clean everything out. Why? I don't understand that. You've got the 3 grams of lauric acid you want in there. You don't need to dump it out. All you have to do is put it back in the hot water and get it to dissolve again. While you're doing that, well, put it in the test tube rack. Don't put it in the hot water and let it get too hot. Put it in the test tube rack. Go over and mass out 0.5 grams of the benzoic acid. Again, it's not that you have to have absolutely 0.5 grams, but you need to know exactly what it is. Put that in a weigh boat. Take your lauric acid test tube and transfer that 0.5 grams into the lauric acid test tube. You've already got 3 grams of lauric acid in there. There's no sense in doing it again. Yes, when the benzoic acid goes in, it won't immediately dissolve into the lauric acid because it's solid, but you're going to heat it up to where it dissolves, and when you do and stir it with the thermometer, the 0.5 grams is going to dissolve in the lauric acid. So do that. Put it in there, get it heated up in the hot water to at least 80 degrees, stir it around with your test tube, get that benzoic acid to dissolve in there, take it out, keep stirring it, do the same thing. Record the temperature. Now, one thing, when a pure substance freezes, it's going to hold its temperature. The temperature is going to come down, and then it's going to be constant. And the reason it's constant is that something is offsetting the loss of energy from the test tube, right? It's out in the temperature of the test tube is higher than room temperature, so it's losing energy to the room. So what's offsetting that loss of energy? Well, you're forming intermolecular forces. And you know when you form a bond, that releases energy, right? If it takes energy to break a bond, it must release energy when it forms a bond. So you're forming not bonds necessarily, but you're forming intermolecular forces, which is kind of a bond, and that's releasing energy. And the formation of that intermolecular forces is offsetting the loss of energy that goes out of the test tube, so the temperature remains constant. So you get those 4. When you have a substance that has a dissolved solid in it, then it's a little bit different. As the solid pure substance freezes, it pushes out the solute so that you have freezing of a pure substance, and the solute concentration in the remaining solvent gets more and more concentrated. Well, what happens with the colligative properties when the solute is greater? It pushes the freezing point down more and more. So what typically happens is you'll see it start to form crystals, but the temperature will keep going down very, very slightly. Still be very careful with your measurements. Take your measurements until you get 4 that are exactly the same. Then just do it again. I know they say add 0.4 grams one time, clean it out, add 0.5 grams the next time. There's no sense in doing that. Just take your compound again, put it back in the hot water, warm it up till it's liquid, mix it up really well, get it to 80 degrees, take it out, stir it up, cool it down, do the second data table, both of them with 0.5 grams. I've put up a data sheet that you can use up in Canvas that has 0.5 for each one. Take that data, do the calculations that you do, that they have inside there, and then just take the mean or the average of those two, right? The average is just add them together, divide by 2. Take the averages for those. It'll be so much easier for you. Now you've got a test tube that has the lauric acid with the benzoic acid in it. You want to get rid of it. Don't dump it down the sink. Put it back in the hot water. Get it to be liquid. Take a paper towel and crumple it up or something and put it like in a paper bag. You can dump that in there and it will solidify into like a waxy substance, and then you can put that in the trash. And then when you clean out the test tube and the thermometer, use hot water and lots of soap, because the waxy substance will dissolve in soap. That's what soap does. Soap dissolves oils and waxes. Water does all the cleaning for the most part. Soap just helps with oils and waxes. So clean everything really well with hot water and soap and get it all cleaned out. And like I said, if you've got like a plastic cup or something, you can heat that up till it's liquid and dump it in the plastic cup and then clean everything out afterwards. Just don't dump it down the sink and plug up your sink. All right? If you have any questions about the lab, if you have any questions in the changes, once I get this video loaded, I will send out an email explaining everything. But if you have any questions, email me and ask me. We'll have office hours on Tuesday. We can talk about any problems you may have. Other than that, stay safe. Good luck.